Welcome back to this third week of lecture series on principles of polymer synthesis. This week what we are going to discuss, the topic is the principles of radical chain polymerization. So, this is lecture number 11. Before I go into the principles and discussions of examples of chain polymerization, what I think will be useful is to recap a little bit the key concepts that were taught in the previous week. So, previous week, the theme of the previous week was step polymerization. So, I will write down here some of the key points and maybe a short explanation thereof will be provided again as a kind of recap of the previous week's lecture. So, what we discussed in the previous week was the principles of step growth polymerization. So, certain key concepts that we discussed are the following, that step growth polymerization, basically you know the functional groups of the monomers, they are reacting stepwise, and the high molecular weight, in fact let us not say high, let us say molecular weight of the polymer develops slowly, and you get high molecular weight only towards the end of the reaction, high molecular weight only at very high conversion. Typically you have to go beyond 99%, at least you go to 99%, and we also introduced this idea of degree of polymerization. Mainly we discussed the number average degree of polymerization, and this is related to your average molecular weight, in this case the number average molecular weight by this relation, where M0 is the average molecular weight of the structural units. So, if you have two structural units that are making up the repeat unit of the polymer, then you have to add the molecular weights of the two and divide by 2, because it is the average molecular weight of the structural unit. And so, if x n is developing, accordingly your m n also will develop, the high x n will mean high m n. So, these things we discussed, and also what we discussed is that these reactions typically self catalysis you can do. Say you are reacting an acid, diacid with a diester, you can do a self catalysis, which means the starting acid itself will catalyze the reaction. So, if you are doing self catalyzed reaction, then your x n bar square will vary according to this kind of equation with respect to T, and if you are doing say external catalyzed reaction, external catalysis, so you are adding a small amount of mineral acid as the catalyzer, then your x n bar will vary with T linearly. And we also argued that since your x n bar square is varying with T when you have self catalysis, so that means as the time progresses, the development of x n bar, that means the number average degree of polymerization, and in turn the molecular weight of the polymer, the development will be much slower than if you compare the situation with external catalyzed reaction, where your x n bar is developing linearly with T, not the square of x n bar. So, for all practical purposes, external catalysis has to be preferred, otherwise you have to actually wait for long time to get the desired molecular weight, and so this kind of process then is not industrially favorable. And the third point that we mentioned is these reactions are basically equilibrium reactions. So, the byproduct, say you have a small molecule that is being produced, say water is being produced when you are reacting an amide and a diamine with a diacid to prepare polyamide, or when you are reacting a diacid with a all dialcohol to prepare polyester. So, small molecules are being produced, say water, that you have to remove so as to drive the reaction forward. If you do not remove that, what you will see is that when equilibrium is reached, and that particular conversion, that will be typically lower than your say 99%, it may be 90%, it may be 80%, depending on the equilibrium constant value. So, equilibrium constant value has to be very, very high in order to get molecular weight of any appreciable importance. So, and typically the equilibrium constants for many of these step polymerizations do not go to that kind of range. So, closed system reaction then is precluded, means you do not do. So, what you have to do is open system reaction, and we did a calculation to also demonstrate what should be the equilibrium concentration of water in order to get the desired molecular weight in such situations, which means you have to remove that much of water, you have to remove a certain amount of water to get to that particular equilibrium concentration, corresponding to which you will get the xn bar value, which is a degree of polymerization value, and corresponding molecular weight you can calculate. And we also argued that in this case also, if the equilibrium constant is higher, that reaction is easier to perform, because then you have to, the equilibrium concentration of water that is required to get the same value of the degree of polymerization. If you compare, say you have a target of an xn bar value, say 100, and then you are comparing two reactions which have different equilibrium constant values. So, the reaction for which the equilibrium constant value is higher, you have to actually remove less water in order to get to that particular xn bar value. So, these things all we have discussed, and afterwards we talked about the molecular weight distribution. Molecular weight distribution, in order to get an idea of that, we had a statistical approach largely developed by Flory. And so, with this approach we got expression for number fraction distribution. So, number fraction distribution and weight fraction distribution that we will observe for step polymerization reactions. And ultimately from this we found that even at very large conversion, number wise, if you look at, you still have the number of monomers the most, even if the reaction has progressed to a large extent. However, if you look at the weight fraction distribution, the contribution towards the total weight will be the highest from the highest sized polymer. So, even though the monomers are the largest in numbers in the total polymeric system, their contribution towards the total weight will be very low. That means, the weight fraction of the monomers will be negligible. So, those things we discussed, and then we came to a very important conclusion from there, that the PDI, polydispersity index, which is your weight average molecular weight divided by number average molecular weight, which is nothing but the ratio is basically equal to the degree of polymerization, weight average degree of polymerization divided by number average degree of polymerization, which was 1 plus p. So, p being the conversion. So, which means if you add this situation with this situation where you have to actually go to very high conversion, p has to tend to 1. So, that means in order to get any step polymer which is of practical utility, that means which has very high molecular weight, the kind of molecular weight that actually you desire for the applications, the PDI has to be close to 2 and not 1. So, basically the polydispersity is high for this kind of system. Next, we also discussed a very important side reaction, for step polymerizations, which is cyclization reaction, and we discussed the thermodynamic versus kinetic factors. So, certain ring sizes will be thermodynamically more stable. So, there will be more chance to form those rings and stop the polymerization prematurely if you look at the thermodynamics, but also you have to look at kinetics, that is if you are going to very big ring size, maybe the thermodynamics favors that, the stability is quite high, but the kinetics does not favor, because both ends of a long polymer chain have to come together, that probability becomes lower, because the polymer can have many more conformations in which the two ends do not come together than those conformations which will directly conform to the situation where the two ends will come together. So, these things we discussed, and finally, we talked about interfacial polymerization, where we told that if you are actually doing the reaction at the interface of two solvents and your two reactants, there are two monomers which contain the two functional groups that will react with each other. They are basically in two different solvents which are not miscible, and they will diffuse towards the interface and the reaction will happen at the interface. And as an example, we talked about polyamidation reaction, where you are using a diamine, you are reacting there with a diacid. Instead of a diacid, you are taking a diacid chloride here, and if you are taking a diacid chloride, so that carbonyl group is activated, it is more electrophilic, and then the reaction proceeds at a much higher rate, and the temperature that you have to use for these reactions are much lower than your typical polyamidation reactions. So, basically you can do many of these reactions at room temperature when you have actually activated the acid, and these kind of reactions you could do at interfacial as an interfacial polymerization. And we also told that polyesterification is typically not done as an interfacial polymerization, because the equilibrium constant, the kinetic factors, say the rate constant for that reaction between a diol and a diacid chloride, even though it is significantly higher than the rate constant of the reaction between a diacid and a diol, because you have activated your acid by formation of diacid chloride, still it is much lower, orders of magnitude lower than if you compare the corresponding reaction for the polyamide formation, that is the reaction of a diamine with a diacid chloride. So, if you are employing interfacial polymerization for a polyesterification reaction, the chances are that your acid chloride, since it reacts much slower with the diamine, it will be exposed for a long time towards the aqueous base which is present in the aqueous phase, and then it will be hydrolyzed. So, the reaction, so the molecular weight development will be severely hindered. So, those kind of reactions then you do not do as interfacial polycondensation or interfacial polymerization. So, that concludes our discussion of the key points for the last week. So, now we will come to the theme of this week, which is chain growth polymerization. Mainly we will talk about radical chain growth polymerization as far as discussing in detail the main principles that are concerned. Okay. So, let us go into the theme of the things. So, chain growth polymerization, it is different from step growth polymerization in a way that basically you have a reactive species that is there at the end of a growing chain, and then the monomer molecules, they will add successively to the end of that growing chain in very fast reactions. So, high molecular weight. So, this is basically a progressive growth of the chain at a high rate, and high molecular weight will be produced at very early instant of the reaction, unlike what happens in step polymerization. So, in step polymerization the molecular weight develops more slowly. In chain growth polymerization, high molecular weight species will be present at a low conversion itself for this particular reaction. So, what will happen is that at any point of time, if you are looking at a say step growth polymerization system, you will have different oligomers present, almost no monomer is there, and say in terms of the weight fraction distribution if you look at it like this. So, you have all different species present, and the very high molecular weight species that develops slowly, only that develops to an appreciable extent towards the end of the reaction when a high conversion has been reached. In contrast, for the typical chain growth polymerization reactions, already you will have a very high molecular weight species at a quite low conversion. So, if you take the reaction mixture and you analyze the system, you will see a high molecular weight species that is present. You will have monomers present, you will have the reactive species, reactive, say you are doing a radical initiation, you will have radicals present and you will have monomers present. So, the radicals will be reacting with the monomers and then they will be growing the chains. So, that is the difference, that very high molecular weight is already produced and more number of high molecular weight species is being produced as the reaction is progressing. That is your chain polymerization. So, let us do a schematic discussion of this particular process. So, the general nature for this reaction is that you have an initiator, let us say I am putting it as I here, you have an initiator present. This initiator, of course, it initiates the polymerization, that is why the name is initiator. So, this will actually dissociate into reactive species. So, R star I am putting. Now, this R star, this reactive species, this star is a quite general designation here. This species could be an anion, in that case you have an R minus, it could be a cation, it could be R plus in that case, or it could be a radical. So, you can actually have three kinds of chain growth polymerizations: anionic polymerization, cationic polymerization and radical polymerization. So, if it is a radical, it is like this. So, in general what you will have is you have actually produced this initiating reactive species, and this reactive species will react with your monomer. Typically they will be monomers like this, say you have a vinyl monomer, Y is some other group. Now, so it reacts with this monomer and produces a species like this. So, this star that was there on R, the reactive center, that is now shifted to this place. So, this particular species is your chain initiating species. So, this is the initiator for the reaction. These are different terminologies that you are using, as long as you understand, it will not matter in the end. So, now this particular species will add to another monomer molecule to produce something like this RCH2 CHY, then CH2 CHY. So, this is the initiation step. So, the initiation step has two stages. In the first stage, the initiator is decomposing or dissociating. In the second stage, that reactive center, that reactive species that is produced from the initiator is reacting with the monomer, and then this stage onwards is propagation. Once this particular species is formed, reactive species is formed, this is propagation, because this reaction can repeat several times. You can add several monomers. So, you have a chain that is starting to grow, and at the end of the chain there is this reactive species, and all the monomers will successively add to the end of the chains to grow the length of this chain, and these reactions are typically very fast. So, that a very high molecular weight chain will develop quite quickly, typically at an early stage of the conversion. So, like this if you do, then you can draw the repeat unit, the complete polymer structure like this CH2 CHY. So, this will be the repeat unit M, and at the end of it you will have CH2 CHY star, and then somehow you may need to terminate this growing chain by scavenging this reaction center. So, those things we will come to it after. Now, when you are talking about initiators, so if you have, let us say you are doing a radical polymerization or cationic polymerization and anionic polymerization, and this is your starting monomer. So, this starting monomer, I mean depending on this Y, that will be this Y will be dictating whether this monomer will be selective to an anionic polymerization or cationic polymerization. Typically radical polymerizations you can do with many of these monomers, but it might be selective to either one of them. Say for some of the monomers you cannot do cationic polymerization, for some of the monomers you cannot do anionic polymerization. So, a typical example would be something like this. So, let us say you have CH2 CHY, this is your monomer, and this Y could be an electron withdrawing group. Say you have CH2 CH, let us say you have a nitrile unit. So, this nitrile can withdraw electron through resonance effect. So, that if you are doing an anionic polymerization, say in that case your initiator species will be R minus, your initiator species will be R minus. So, that can attack here, and you know if you compare with this, then basically your negative charge goes here, and that negative charge can be stabilized by this electron withdrawing groups through resonance effect. How? So, the negative charge goes here and that can be further shifted here like this. So, overall I can do like this. So, basically you can have a resonance stabilization of the negative charge that is growing here, because that is being presented here because of the anionic initiator. So, then if you have Y which is electron withdrawing, it can stabilize a negative charge development on this particular carbon, and that way these kind of materials, these kind of monomers can undergo anionic polymerization. Will they undergo cationic polymerization? Answer is no, because a positive charge here cannot be stabilized by electron withdrawal. In fact, that will be further destabilized by electron withdrawal. Of course, through resonance you do not shift that, maybe through inductive effect you can shift that, that means it is electron withdrawing unit because of the electronegativity through bond effect, and then it will destabilize further that positive charge. So, this kind of monomers then cannot undergo polymerization through cationic polymerization means. If you have a monomer like this CH2 CHOR, if you have a monomer like this, now this kind of monomer your oxygen can actually donate a lone pair like this, and you may have a negative charge here. So, if you are doing a cationic polymerization, so you have a resonance structure, in fact this is resonance structures which will be CH2 minus CHOR plus. So, here if you are, so for this particular monomer if you are using say a cation as the initiator, say you are doing a cationic polymerization, then that is highly favored because electron density on this carbon is quite high. So, that can react with this positive charge, and if you are doing an anionic polymerization for this, it will not react through anionic polymerization, because the electron density can be shifted from oxygen to here. So, that means if you have an electron deficiency here to start with, that can be stabilized by electron donation, but if you already put an electron density here by an anionic initiator species, then that cannot be stabilized by electron push to this site, that will be further destabilized. So, these materials cannot undergo then anionic polymerization, they will rather undergo cationic polymerization. But if you look at radical polymerization, many of these materials are not selective, means they can be actually subjected to radical polymerization, because the stabilization of the radical is not a charged species unlike a cation or an anion. So, the stabilization of the radical can be affected by both electron withdrawing as well as electron donating units. So, for example, if you take this particular monomer and if you initiate the polymerization with a radical, so then what happens is that, so the radical comes here, so it is half arrow because it is one electron. So, it will be like this R CH2 CH dot C triple bond N, and now this radical can be stabilized. So, so this electron goes here. So, half arrow means one electron, full arrow means two electrons. So, one electron comes here and one electron can go there, and then it can have this kind of structure R. So, I will just draw this structure here, then you can have this kind of structure R CH2 CH double bond C double bond N dot, that is how it can be stabilized. So, it is less selective to the radical polymerization. So, whether you have an electron withdrawing group or electron donating group, you could typically do a radical polymerization for those kind of monomers, but the monomers will be highly selective to either anionic or cationic polymerization, because these are positively charged species initiators. So, that will generate positive or negative charge in the propagating species. So, that charge in the propagating species has to be stabilized by Y. So, if it is a negative charge, then an electron withdrawing Y will stabilize that negative charge, so that an anionic polymerization could be favored for an electron withdrawing Y group here. If you have an electron donating Y group here, then it will actually stabilize the positive charge that is developing in the polymerization process in the propagating species. So, that way if you have an electron donating group here, this particular monomer will rather undergo cationic polymerization than anionic polymerization. And as I told, whether you have an electron withdrawing group or electron donating group, both can basically stabilize your growing radical species if you compare with cationic or anionic, because radical species are neutral species. So, radicals can be stabilized like this. Similar kind of structures you could draw also when you have electron donating groups like this, that can stabilize the growing radical. Okay. So, what are the kinds of initiators that you could use? For from now on, what we will do, mainly we will be talking about radical polymerization. So, one of these, because if you are looking at anionic and cationic, probably those things we will come into little bit more detail if and when we discuss about the corresponding preparation of the industrial polymers. But for the time being, we will keep our attention to the mainly to the radical polymerization reactions. So, the initiators that you could use, they could be thermal initiators, means this reaction that I is forming R star, in this case R dot, this reaction could be thermally initiated. Your initiator could be decomposed by heating or dissociated by heating. So, mainly the kind of bonds that will be present in the initiators that can be used for thermal initiation will be like peroxo linkages, or you can have linkages like sulfur or nitrogen oxygen, those kind of linkages you can have. And so, let us say you can have a peroxide like this, okay. So, you can have a benzoyl peroxide, or you could have an alkyl peroxide, let us say, and these will decompose at this, rather let us say dissociate at this particular bond when you heat them, and it will produce this kind of radical, initiating species. Or you could also use, so this is peroxo linkage, you could also have say hydroperoxide, there also you can have a peroxo linkage, say let us say tart butyl hydroperoxide, it can break here. Or you can have an azo linkage. One of the most common thermal initiators that are used for radical polymerization is azo-isobutyronitride. So, which is nothing but you have CH3 and then you have a nitrile unit here, and then N double bond N, and then you have CH3 CN. So, the nitrogen will evolve and you will have radicals like this CH3 whole twice C Cn dot this is also a thermal initiator. So, typically the temperatures might vary, say 60 to 70 degrees you might have to heat for AIBN in order to have a dissociation of these bonds, or for some other systems you may have to heat to 120 130 degrees Celsius, that depends on the choice, the type of initiator that you are using. Another kind of initiation that you can do for radicals is, say you can have redox initiators. So, basically you will have an oxidation reduction reaction that produces radicals. So, oxidation reduction reaction that will produce radicals. So, and typically for this kind of reactions you can use a wide range of temperature, even close to 0 degree Celsius or say 50-60 degree Celsius. Okay. And let us say some example, say if you have peroxide, the peroxide linkage if you have in the molecule, and in combination with a reducing agent that can produce a radical. Say if you have hydrogen peroxide with a reducing agent ferrous ion, it can produce OH minus plus OH dot plus Fe3 plus. So, this is being oxidized and this is being reduced. So, you have OH dot, you have a general peroxide linkage, then also you can have RO minus plus RO dot plus Fe3 plus. So, finally, you can also have photochemical initiation. Photochemical initiation. So, typically they do not require any heat for the dissociation of initiator. What you do is that you supply the energy with a light quantum. So, you have a reaction system and that you can use, say UV visible light, say the UV end spectrum or the only visible spectrum light, and then you can create radicals. So, typically you are using ketones like this, one aryl group and another kind of aryl group, aromatic units. H nu indicates you are putting a light, and then you can have this kind of stuff, CO dot plus air dot, air prime. Okay. So, that tells you about different kinds of initiators that you can use. So, for these different kinds of initiators, when you are doing the kinetic analysis of the reaction, the analysis will vary. So, from now on what we will do is typically our concentration will be gauged towards reactions where you are using thermal initiators, and in the next class we will start with kinetic analysis of radical polymerization where you are using thermal initiators. We will come back to photochemical and redox initiators when we talk about the effect of temperature on the reaction rate or the effect of temperature on the molecular weight of the polymer later on. So, that concludes our today's class. Thank you very much and see you in the next session.